In this section, I'll discuss trajectory and range in a medium for which fluid resistance is linear in the velocity. Recall from section 2.2 that the dynamical equations describing linear fluid resistance look like this. So we have here the acceleration along the x direction, and that's just the fluid resistance, which is proportional to the x velocity. Here is the acceleration along the y direction, and again we have the fluid resistance proportional to the y velocity, but in the y direction we also have a downward gravitational acceleration. The book shows that the solutions for x and y as functions of t for motion in a linear fluid is shown by these expressions. So here's our solution for x of t, here's our solution for y of t. And let's plot qualitatively what we expect these solutions to look like. In section 2.3, what we're interested in is figuring out how far would our projectile travel along the x direction in the time it takes for the projectile to go up and come back down. In other words, for y to go from 0 up and then back down to 0. So to get an intuitive sense, let's plot the two solutions here. Looking first at our x solution, it's written up here again. We can see at time t equals 0, our exponential over here, that's just going to be equal to e to the 0. E to the 0 is just 1, and so this whole term in parentheses is just going to be equal to 0. And so that means that x at t equals 0 is by definition x equals 0. So that's easy. And then as t gets bigger and bigger, this term here, the exponential, is going to get smaller and smaller, because e to the minus t over tau, that's going to get to be closer and closer to 0 as t gets bigger and bigger. And so what we expect our solution for x to look like as t goes to infinity is that this term's going to go to 0. That means we're just going to have this term here in parentheses, the 1. And so x is just going to approach vx naught times tau, just a finite value. So let's imagine that vx naught times tau is here, vx naught tau, and the curve x of t is just going to approach that value asymptotically. So it's going to get closer and closer and closer without ever actually reaching that value as t goes on to infinity. Now we know for the case of a projectile launched from the ground, y equals 0, upward and then falling back down, that the projectile is not going to fall, is not going to move for an infinite time. So x is not going to be allowed to actually move along until t equals infinity. It's going to reach some finite value at some finite time. So we'll say t stop here. And so the key is we need to know how long does the projectile take to go up and then come back down. And so to figure that one out, let's go look at the y solution. So here's our y solution again. The y solution is a little more complicated than the x solution because we have the gravitational acceleration, which wants to pull the projectile down. Also, we have the linear air resistance, which wants to push the projectile down as the projectile moves up, but then it wants to push the projectile up as the projectile is falling down. And so that term, that combination makes the solution for y a little more complicated. With these two terms here, we have a term here that looks a lot like the solution for x, and then we have this term over here. Now, when t is 0, we can plug in t equals 0 to these equations, and what we find is, again, this term in the parentheses is going to be 0, this term over here is going to be 0, and so t equals 0, y is going to be 0. So we start at the origin. Then as t increases, we get some interesting behavior. When t is small, this term is going to be small, as is this term. But this term is actually going to be bigger than this term over here if the initial velocity in the y direction is non-zero. And so that means that initially our projectile is going to move up. But eventually, y will reach some maximum value. Basically, this term in the front here is going to reach a maximum value of about equal to this over here. Eventually, this term is going to become very small compared to this term, and so y is going to max out at about this. And at that point, this term begins to dominate. So y will reach a maximum value, and then the second term over here will dominate, and you can see that since it has a minus sign, it's going to drive y toward negative values. And so y is going to go up and then come back down. And so when we're thinking about the distance over which our projectile moves along the x direction, what we're interested in knowing is how long does it take the projectile to go up and then come back down? What is this stopping time? And so the trick is we need to figure out at what times is y equal to 0. So we know y is equal to 0 when t is equal to 0. That's one root for this equation. But there's another root over here where y is bigger than 0. Excuse me, where t is bigger than 0 and y becomes 0 again. So let's see if we can figure that one out using this equation here. And so at the point at which the projectile strikes the ground again, y is equal to 0, which means that this right-hand side has to be equal to 0. And so now what we'd like to do is to solve for t such that the left-hand side of this is 0. And what we find is we get an expression that looks like this for t. So there's the v terminal times t, that's that term over there. We've brought that over to the left-hand side. And then on the right-hand side, we have everything left. And you might notice a problem right away. What we have is an equation in which t appears here, and then t also appears as the argument to an exponential function. And so this type of equation is referred to as a transcendental equation. What it means is there is no closed form analytic solution. In other words, we can't write the exact solution for t using pencil and paper. There are different ways to solve transcendental equations. Very often you can just plug them into computers and solve them numerically. But before the advent of powerful computers, that was very difficult, and so there are a number of analytic approximations that allow you to solve for transcendental equations like this. And so what we're going to do is follow the book's lead and apply an approximation to arrive at an approximate solution for t when the projectile strikes the ground again. And from that approximate solution for t, we're going to work out what the range is, the distance over which the projectile travels during this time. So the first thing we do is go back to our x solution, and we say that x travels a distance r. We'll call that r range, and so that's going to be equal, of course, to the solution on the right hand side. And so now what we're going to do is we're going to solve this equation for t in terms of r. So first let's divide through both sides by vx naught over tau. So vx naught times tau, and that's equal to 1 minus e to the minus t over tau. We're going to subtract this from both sides and add this to both sides, and so that will give us e to the minus t over tau is equal to 1 minus r over vx naught tau. And then finally we can take a natural log base e of both sides, bring over our tau, and what we'll find is that we can replace t with this expression, minus tau times the natural log of 1 minus r over vx naught times tau. And you might get worried here that we have a time t which has a minus sign in it when we're looking for a positive t. Well, keep in mind here that the number inside of here, 1 minus all of this, is going to be a number smaller than 1. And the natural log of a number smaller than 1 is itself negative. And so this whole thing is going to work out to be positive. So we'll get a positive time. And so now what we'll do is we'll plug this into our expression for y of t, and what we'll get is an expression for y as a function of the range r, which we can then solve for the range r. And so making that substitution, we find that y is going to be equal to all of this involving r, and when x has traveled that distance r, y is by definition 0. So this whole thing is just equal to 0, and so then we get this expression for r, which looks like this. So all of this times r is equal to v ter tau natural log 1 minus r over vx naught times tau. And you can see again we end up with this transcendental equation. We've got r over here, then the log of something that involves r. So strictly speaking, we can't solve for r. This is another transcendental equation. So now we're going to apply these approximations that allow us to get an approximate solution for r. And here's where we bring in our physical reasoning. We expect, or at least we're going to assume, that the air resistance in the problem is small. It's not that big. And what that means is that the range over which our projectile travels is going to be almost exactly what you would get if there were no air resistance. Okay. And in other words, that has the consequence that tau, the time scale over which the viscous force acts, tau is going to be very large. So we'll say tau is going to be much, much bigger than t. Or we can write this another way. We're going to say that r divided by vx naught times tau, we're going to say that this is very small, much, much less than 1, because the viscous resistance is going to be small. And so what that's going to allow us to do is write an approximate expression for this log that will allow us to solve for an approximate solution for r. So let's see what that looks like. Okay, so we're going to rewrite the term that we're interested in here. So we've got natural log of all of this in here, and we're going to define all of this to be the same as log of 1 minus epsilon. So essentially we're defining epsilon to be equal to that stuff, just to encapsulate it all into one term. And now what we're going to be interested in doing is considering epsilon to be small compared to 1, and then we're going to do a Taylor expansion of this expression here. Now you may recall that if you have some function f of x, that the Taylor expansion of that function is given by the Taylor expansion of the function f of x at some point x naught, near some point x naught, is given by the function itself evaluated at x naught plus the difference between x and x naught. So x is the place where you want to evaluate the function now, and x naught is the point at which you're grounding the function. So x minus x naught times the first derivative of f with respect to x evaluated at x naught plus 1/2 x minus x naught squared second derivative of the function evaluated at x naught, and so on. You basically just keep doing this. You'll refer to your textbooks to recall the exact Taylor expansion. And so what we're going to basically do here is apply a Taylor expansion to this. So let's see what that looks like. Okay, so here we are, doing the Taylor expansion of log of 1 minus epsilon, where epsilon is small. So the first thing we're going to do is evaluate log of 1 minus epsilon at epsilon equal 0. That's going to be the log of 1. So natural log of 1 is just 0. Plus x minus x naught, which in this case x naught is 0, and x is just going to be epsilon. So we're just going to get epsilon times the first epsilon derivative, evaluated at epsilon equals 0, of log 1 minus epsilon. Okay? And so the derivative of log 1 minus epsilon is going to be, remember, 1 over 1 minus epsilon, and then you have a minus sign here, so you're going to put a big minus sign up front here. Okay, so the epsilon derivative of log 1 minus epsilon is minus 1 over 1 minus epsilon, and remember we're going to evaluate this at epsilon equals 0. So evaluated at epsilon equals 0, this is going to be equal to minus 1. And we're going to keep doing this for the next several terms. The book actually expands out to an epsilon cubed term. I won't bother to show that here because the pattern is more or less the same. And now let's go ahead and skip forward to the full expression for log 1 minus epsilon for when epsilon is small. Okay, so the book has this expression for log 1 minus epsilon when epsilon is small. So here's our Taylor expansion out to third order, we would say, third order in epsilon. And with epsilon small, that's a pretty high order expansion. Recall, epsilon is defined to be equal to our range divided through by the initial x velocity and tau. Okay, so now we come back to our log expression. The original log expression, and we're going to say that that's approximately equal to minus r over Vx naught tau plus a half r over Vx naught tau squared plus a third r Vx naught tau cubed. Okay. And now let's put this expression back into our overall expression we're trying to solve. Remember, we're trying to figure out what this range is by evaluating our original equation at y equals 0. So here's our expression. We plug everything back in to the original equation. Now the book goes through some wicked algebra. I'll try to walk you through some of this because it can be a little confusing. First of all, you can see that when we multiply this by this term, we're going to cancel out these taus, and we're going to be left with minus the term we get when we multiply these two guys by that. So the idea is that this term is going to cancel with this term here. Okay, and then we're going to be left with the following. This is what we get on the bottom line here. We're left with this term from here. Then we have this term from here. You can see that we multiply through by vter. Get that. Cancel out one of the taus here. There's a tau squared, so we get a tau on the bottom. And then we multiply this guy through by this. We get this term down here. We cancel one of the taus, so it's tau squared instead of tau cubed. We have Vx naught cubed, and then vter on the top, r cubed. Okay. The next thing we can do is divide everything through by a factor of r. So we see r in 3 places at least. So here's r there. We're going to cancel that one out. We'll get rid of the r squared, so we just have r in that term. And this one, it'll be just r squared. Okay, so let's clean things up. Alright, so we have this now. Here's our first term, the second term, and our third term. The next thing we're going to do is multiply everything through by Vx squared. Okay, so that's going to get rid of one of the Vx's here. It's going to put another Vx up top here. We also are going to multiply through by 1 tau. So we're just going to multiply through by that tau. That'll get rid of a tau here, and it'll put a tau up here. And then finally, we're going to divide everything through by our terminal velocity. So that'll get rid of terminal velocities in the numerators in those two terms, and it'll put terminal velocity in the denominator in the first term. And so we get this. So that's our first term on the left, second and third term. You may recall that the terminal velocity divided by tau, that's just equal to the gravitational force, gravitational acceleration. And so this term here turns into 1 over g. Then the book goes through and it multiplies everything through by 2 to get rid of that 1/2. And finally, we're left with the following. This equation right here. Now the book, now this is basically a quadratic equation in R. And so you could use your normal quadratic equation, negative b plus or minus square root b squared minus 4ac all over 2a, to solve for R. But the book does something a little tricky here, a little confusing. It rearranges this equation so that you get R on one side, and you've set that equal to 2 Vx naught, Vy naught over g minus 2/3 all this business in here times R squared. Okay. Now the book has pointed out by now that this distance right here, that range is what you get for a projectile moving in the absence of air resistance. So that's the answer you get in your sort of Physics 101 class for projectile range when you ignore air resistance. So the book defines that as R vac. And because we've assumed that the drag is small, remember we've assumed that the drag timescale tau is really big, R at the very first order is going to be equal to the vacuum R. So in other words, this term dominates. This term over here is much smaller. And so the book does this funny thing where it actually plugs in R vac for this term here and for this term here, and then solves for R in terms of R vac. Now why can you do that? Well, imagine that we didn't do that. Imagine that we kept this R here and didn't plug in R vac. Okay? Then what we would get is, for our actual value of R, would be R vac plus a small correction, call it delta R. Okay, so this term here is small compared to this. R is almost exactly R vac, but then it's got this small correction. And you can imagine that if we took this R vac plus delta R and plugged it in here, we'd basically just get R vac squared with a small correction on top of it. And so that small correction, that's really what we're trying to solve for. So the fact that this term over here is R squared means that the departure of R from R vac, that small departure, contributes a very tiny correction to the R squared term. And so, as the book suggests, we can basically plug in R vac for this R and get a reasonable approximation to the right value for the projectile range in the case of air drag. And so that's what the book is basically doing. We'll come back to this idea again later in the semester, where you can actually kind of iteratively solve an equation by plugging in an approximate answer on one side and then solving for the next higher order answer on the other side, and do that over and over again actually until you get a very accurate answer. So in any case, this gets you to the answer that the book has for R, which is related to R vac, and then there's a small correction term you see.